I'm Tom Sandry, Director of Workforce Development at Vector Power. I get a lot of questions about the practical use of partial discharge testing in a field environment. What we hope to accomplish today is for you to understand the difference between factory testing and the unique challenges we face when testing those same cables in the field. Now, PD measurements are utilized in various environments, including the field, laboratory, and factory for multiple purposes, such as qualification, quality assurance, and condition assessment. Understanding the fundamental differences among these environments is essential, as the metrics used and the strategies for noise mitigation can vary significantly. The main difference between field tests and factory tests lies in their application. Factory tests are conducted on unaged cables or accessories, while field tests are carried out on entire cable systems consisting of cables and accessories all installed together. Field tests involve systems with new and aged components, making them more challenging. Partial discharges are tiny electric sparks that can occur at defects in insulation, along interfaces, or surfaces between a conductor and a floating conductive component, not connected to the high voltage conductor or the ground, or between floating conductive components. When the intensity of the electric field is strong enough to ionize the medium surrounding these components, partial discharges will happen. These discharges do not completely bridge the insulation between the conductors. The defects may be located entirely within the insulation, along the interfaces between different insulating materials, or along the insulation surfaces, such as terminations or potheads. The characteristics of partial discharge depend on various factors, including the defects, type, size and shape, and location, insulating material, applied voltage, and the cable temperature. These characteristics can change the magnitude or frequency over time. The potential damage caused by partial discharge varies significantly. It could be negligible in some cases, while in others, it may lead to failure within seconds or over several years. Advancements in digital electrical measurement technology, both in the time domain and frequency domains, have enhanced the effectiveness of PD measurements. This is particularly true in environments with high background noise levels that operate within the same frequency band as the PD signals. As a result, there has been a growing trend in conducting PD measurements on cable systems in the field, especially on medium voltage systems. Let's really understand the physics behind partial discharge. Partial discharge occurs as a Townsend discharge within a small cavity. This process involves gas ionization, where a small number of free electrons, when accelerated by a sufficiently strong electric field, will lead to electrical conduction through the gas due to avalanche multiplication. The voltage at which the discharge begins is described by Paschen's law, with the key factor being the product of the void size, or diameter, d, and the internal pressure, P. The constant beta and chi are specific to the gas inside the void. Now, the Paschen equation identifies several fundamental issues that the cable system engineer using PD testing must understand, including discharges only occur in gaps, And PD testing can only identify voids, not contaminants, unless they later debond from the insulation, creating a void. Voids need to satisfy 3 further conditions to discharge. They must not be filled entirely with a liquid. If they are gas-filled, the gas must be at a low enough pressure for the discharge initiation stress to be at or below the test stress. And third, they must be large enough. Small voids require higher initiation stresses. When measuring PD, 3 prerequisites must be satisfied during the measurement period. The void must be in a state that allows them to discharge. The voltage must be high enough to initiate the discharge, the inception voltage. The PD signal must arrive at the detection in a clearly defined, unaltered, unattenuated, and undispersed state to be distinguishable from background noise as recognized PD signals. Now, let's slow down. Regarding that first point about the state of the void, partial discharge is a stochastic, probabilistic process. Depending on various parameters and conditions, it may or may not occur at a void. Therefore, if no partial discharge is detected, it could mean that no voids are present, or a void exists, but the conditions are unsuitable for discharge. This is particularly important for short measurement durations and the risk of producing false negative results should be acknowledged. Discharge sources can be found at various points within a cable system. However, there are limitations on the number of access points where a user can install a sensor to detect the partial discharge. When a PD event occurs, it generates an electromagnetic pulse that travels as waves through the shield cable system, which functions as a waveguide. Unfortunately, power cable systems are not perfect waveguides, leading to distortion of the pulses as they move away from their sources. This distortion is influenced by several types of cable system losses, which vary with frequency. The longer the cable system, the more significant the distortion becomes. The physical process that contributes to these changes are well understood and include skin effect, dielectric loss, reflection, and radiation. 2 major sources of PD pulse distortion are attenuation, the loss of energy that reduces the magnitude of the pulse, and dispersion, caused by different propagation velocities for different frequency components within the pulse, which smear the original pulse shape. So, let's first address attenuation. Attenuation refers to the loss of pulse energy as it travels over a distance and across its frequency spectrum. In a cable system, this attenuation occurs due to losses in the bulk insulation and the resistance encountered in the conductor, neutral wire, and semiconductive screens. Generally, attenuation increases with frequency, and energy losses can be significant at frequencies in the range of a few megahertz. As a result, fast PD pulses can only travel limited distances due to their high frequency components, as they become attenuated to a level where they are indistinguishable from the background noise. Now let's address dispersion. Dispersion is the phenomena in which the different spectral components of a pulse travel at varying velocities within a given medium. Higher frequency components move faster than lower frequency ones. This variation in speed results in a phase shift for each frequency component of the pulse, leading to a distortion in the pulse shape. Consequently, the output pulse tends to have lower amplitude and longer duration than the original pulse shapes generated at their source. It's important to note that dispersion alters the pulse's shape without causing any energy loss. Now, let's focus on offline testing of partial discharge. Offline testing will require a source of test voltage. Voltage sources must be alternating current and can be characterized as power frequency operating at 50-60 Hertz. Now, this large and heavy equipment is typically reserved for laboratory and factory testing where transport is not a requirement. We also have near power frequency operating in the 30 to 300 Hertz band. The equipment typically consists of an excitation transformer connected in series or parallel with a variable inductance reactor. It is heavy and requires a dedicated truck or van to transport. We also have very low frequency operating from 0.01 up to 1 Hertz. Now, this equipment is relatively light and portable, but may be an additional noise source. Both sinusoidal and cosine rectangular waveforms are available in VLF. And finally, we have yet another alternative to power frequency. We have damped AC, otherwise known as DAC. The equipment is lightweight and portable. It operates with a damped sine wave voltage that ranges in frequency from 30 to 500 Hertz. The frequency can vary based on the cable length and in some cases can be adjusted using an external component such as a capacitor. Now, let's best understand why operating at power frequency 50-60 Hertz requires such large equipment. Well, the reason for large transformers when referring to items like power cables has to do with the capacitance of the load that is being tested. Capacitive reactance, or X sub C, changes as a function of frequency, as we can see in this formula, where F is the frequency of the test voltage and C is the capacitance under test. Therefore, if we were testing a 15 kV rated cable at approximately 10,000 feet in length, the capacitance would be around 1 microfarad. Now, based on the formula, the capacitive reactance at 60 Hertz would calculate out to be 2,654 ohms. To apply the IEEE recommended 22 kV test voltage, it would require a power supply rated for 8.3 amps or 183 kVA. That's going to be tough to fit in your truck. Let's move on to near power frequency, sinusoidal voltage sources. These can replicate the waveform of the operating voltage in the device under test system and allow for increased voltage magnitudes beyond the normal operating levels. NPF voltage sources are defined as sources that generate a sine wave with a frequency range of 20 Hz to 300 Hz when connected to the device under investigation. The equipment typically consists of an excitation transformer connected in series or parallel with a variable inductance reactor. This helps counteract the capacitive reactance of the load. Now, the equipment is still heavy, and it does require a dedicated truck or van to transport. Let's take a look now at very low frequency. The field industry as a whole really loves VLF testing. And the main advantage of testing at very low frequency is that it significantly reduces the size, weight, and cost of the required power supply, and thus offers greater attraction for field testing of medium voltage cables. It also makes the technology more available to a larger variety of clients. So, why is a VLF test set smaller than a power frequency test set? Well, if the test frequency were dropped to 0.1 Hertz, the capacitive reactance, as calculated earlier, becomes 1.6 megohms. Now, we further do the mathematics and we see that the power supply VA requirement has been significantly reduced. Thus, the main advantage of testing at very low frequency is that it significantly reduces the size, weight, and cost of the required power supply, and thus offers greater attraction for field testing of medium voltage cables. Now, we do have a relatively new player in the field, damped alternating current, also known as DAC. These voltage sources are lighter in weight and have lower power requirements than near power frequency excitation sources. The IEEE standard 400.4 addresses DAC voltage testing in the near power frequency range from 20 Hz to 500 Hz. Damped alternating voltages are generated by charging the cable system under test to a predetermined voltage level, then discharging the test object's capacitance through a suitable inductance. During the charging stage, the test object is subjected to a continuously increasing ramp voltage. During the discharging state, the test object experiences a damped oscillating wave, hence damped AC. How about we now talk about what are the resources that we can turn to better understand the complexities, process, and analysis of partial discharge. Among these we have the IEEE standard 400.2 2024. This guide describes very low frequency, or VLF, withstand and other diagnostic tests and measurements performed using VLF energization in the field on shielded power cable systems. Now, in the document we see various key words: cable fault locating, cable system testing, but among those key words is partial discharge testing. Partial discharge testing is actually covered in section 5 of the guide, Very Low Frequency VLF AC Testing, in subclause 5.5, partial discharge tests with VLF sinusoidal waveform. One of the best go-to documents is the IEEE standard 400.3, the new 2022 revision. This guide covers the diagnostic testing of new or service age installed shielded power cable systems, which include cable, joints, and terminations, using partial discharge detection measurement and location. Now again, in the keywords we see various, but among that is offline partial discharge testing as well as online partial discharge testing. Yet another standard we mentioned earlier is the IEEE standard 400.4 2015 revision. This one is for our new player, DAC. The guide outlines the practices and procedures for testing and diagnosing shielded power cable systems rated at 5 kV and above using damped alternating current. It applies to all types of power cable systems designed to transmit or distribute electric power. The goal of the guide is to establish standard practices and procedures for conducting offline DAC voltage tests on installed shielded power cable systems in a field environment. It also provides guidelines for assessing the test results. Hey, let's not forget about our international partners. The IEC 60270. This international standard applies to the measurement of partial discharge that occurs in electrical apparatus, components, or systems when tested with alternating voltages up to 400 Hertz or with direct voltage. A wonderful research paper that I highly recommend everybody get a copy of, the Georgia Tech NETRAC Cable Diagnostic Initiative. Now, NETRAC specializes in collaborative and proprietary research projects in several important industry areas. The results of these projects are used by electric utilities and manufacturers to improve the quality of transmission and distribution systems. And last but not least in our resource references, we have the ANSI NETA acceptance testing specifications and maintenance testing specifications. Well, thank you for your attention, and that's a wrap